Hello, in this video we are talking about convolution and we are starting our discussion here by considering an initial value problem. We already know how to deal with initial value problems with Laplace transforms. But today we're considering something we haven't done before, which is a general forcing function, g of t, on the right-hand side. So like normal, we're going to let y of s be the Laplace transform of y. Now we're going to say this capital G of s is the Laplace transform of g, applying our properties of Laplace transforms and plugging in our initial values. We get s squared capital Y of s plus, sorry, that's a typo, that should be a capital Y of s there, equals, oh, and let me go ahead and change that. There we go. Capital Y of s equals capital G of s. So we can solve for y of s really easily, get 1 over s squared plus 1 times capital G of s. Well, from the table of Laplace transforms, we know that 1 over s squared plus 1 is the Laplace transform of the sine of t. So if we could just very easily take the Laplace transform of the 1 over s squared plus 1, we could get to a sine of t, and we know that that this capital G of s is the Laplace transform of little g, so we could undo that Laplace transform and get back to g. That would be if we had these two things separately, but instead they're being multiplied. So the question here is, how do we find the inverse Laplace transform of the product of those functions, because that's what gets us to the solution of the differential equation. So unfortunately, it's not just the product of the Laplace transforms, but what we can use to get the inverse Laplace transform of this product is we can use a convolution. Now, convolution is defined in terms of this integral. It's for two different functions that are at least piecewise continuous on an interval from 0 to infinity. It's denoted with this little star symbol. So f star g, or f convoluted with g, is the integral from 0 to f, 0 to t, of f of t minus v, g of v dv. So notice, even though we have a t in here, we are integrating with respect to v, so it is okay, or we can integrate with respect to v. T is held as a constant. So for an example, the convolution of t and t squared, we will notate that as a t star t squared. And using our formula, we have the integral from 0 to t of t minus v, since that's what f is, and v squared, since we're plugging v in for that. Well, we can integrate this pretty easily. The easiest way to do it is to distribute our v squared. So we dv squared minus v cubed dv. And then we just have a polynomial to integrate. Notice we are integrating with respect to v. So this becomes a v cubed over 3, and we multiply by t since that's held constant. This becomes a v to the 4th over v. And then we need to evaluate at our endpoints 0 and t. And notice these are values that get plugged in for v, since we were integrating with respect to v. So t gets plugged in there, t gets plugged in here. We end up with a t to the 4th over 3 minus t to the 4th over 2. Those are like terms. We can combine them when we get that our final answer is t to the 4th over 12. So what this means is the convolution of t and t squared is t to the 4th over 12. So one thing to notice here is that convolution, although it is somewhat a multiplication, it is not the same as just ordinary multiplication. So 1 convoluted with 1, or 1 star 1, is equal to t, which is not just equal to 1. And in general, 1 star f for some function f is not just equal to f. So it doesn't satisfy all properties of multiplication, although it does satisfy some. And this theorem lists a few that it does satisfy, one of them being that the order of the convolution doesn't matter. And this can be extremely helpful because sometimes there are certain functions that are easier to substitute in t minus v than others. Like in this case, it was much easier to substitute t minus v into t. because if we had substituted in for t squared, then it meant that we would have had to square t minus v, and it still would have been doable, but it would have been more work. So in this case, whether we had done t squared star t or t star t squared, sorry, I got mixed up on the words there, the order does not matter. You would get the same final answer either way. So that one can be very helpful sometimes. You can also distribute a convolution, so f star g plus h, you can distribute it. If you have three functions that you are trying to find the convolution of, the order again does not matter. And one thing that is always true, if you do f star 0, so you convolute a function with 0, you will always get 0. So it's not true that 1 star f is equal to f, but it is true that f star 0 is equal to 0. And that's where we will break this video for now, and I'll pick up with material continuing on in this discussion about convolution in the next video.